let's start the topic. I just realized there's an AI translation screen here. So previously, I want to speak English, but due to my poor English, I think speak Chinese can be better to use the translation screen. So, but overall, I think I can speak English. So the topic is the best class of training and inference on Ascend. I'm Xiyuan Wang from Huawei. Have over 10 years open source contribution, and now is beyond Ascend antenna. So the topic contains two parts. The first, I will introduce the technical overview and the ecology of CANN. And the next, I'll take VM as an example to show that how Ascend CANN works in inference and training scenarios. Okay, the first one is technical overview and the ecology of CANN. So what is CANN? CANN is short for computer architecture of the neural network. It is helps to enable efficient development of native applications and unleash ancient computing power. So take the picture here. CANN is mainly contains here about hardware and the hardware driver. It mainly contains 4 levels I want to introduce. The first one is GE graph engine. And the second one is Ascend C or C++ operator programming language. And the third one is the operator acceleration library. And the last one is HCCL aggregate communication library. I'll describe them in full detail in the next 4 or 3 or 5 slides. And so it's kind of users, developers, especially developers for Ascend, enable parallel computing acceleration for large language models, and can write the AI models or AI is easily. And CANN is also deep openness and ecosystem compatible. Okay. The last one is beyond the CANN, there is a lot of open source AI framework or AI APIs built on CANN. For example, or support Ascend hardware based CANN. For example, the AI framework PyTorch and some others, for example, ManSpar and so on. CANN works on Ascend directly with CANN. Okay, so before coming into the detailed technology, I'll just show you a brief view. On the left part, it's the general computing database. That means in original scenarios, there's no any accelerators, for example, such as GPU or MPUs. All the calculations runs on CPU. The performance is very bad and speed is slow. So with the accelerators hardware, for example, such as Ascend, we can offloading some computing, CPU computing into the NPU, especially for the vector or cube compute. For this kind of compute, we can speed up it in NPUs because it runs in parallelized computing. And as I said before, there's mainly four important libraries in CANN. The first one is the GE graph engine. As we all know that when we do the inference or trainings for a model, the model is contained by different kinds of operators. And if without the graph engine, if we do inference, we'll take the operators one by one. And in this case, will cost a lot in scheduler, chip, and so on. So it will waste much of time. And with the graph engine, we can set the whole picture into the NPU directive. And in this case, users don't need to care about the data translation between CPU or NPU, and all the computer scheduling between one operator to another operator. So it can speed up the inference or training. And another, the second technical action is about the split diagram calculation. It means that we can make the model into pieces. Because, for example, if there's we take the model of the whole graph, if there's some operators in the graph can't be generated into a graph, they can split the whole picture into one into more some pieces, and for the parts which can run as a graph, they can send this calculation into GPU directive. And for the some small operators, they can run it after the graph actually start. So with this technique, the performance can be improved. The next one is Ascend C or C++ operator programming language. This helps developers to write custom ops easily, just with C or C++ language. So with this language, developers don't need to know the details of the NPU or the details of CANN. They can just write the operators they want, use the high-level APIs. For example, in the right side, users can just call the high-level APIs for example, copy in, copy write, and some others, for example, a stream, an event, maybe you know that in cloud. How is the thing? Okay, the next one is HCCR aggregate communication language. This is a high performance communication language based on Xiyuan AI processor. It contains three features, key features. The first one is high performance site communication algorithms. We know that now the large language models become bigger and bigger. Most of them can't be located just in one in single card. So we have to deploy the models into multiple card or multiple machine. So in this case, we need a communicator library to make the models or data to work together effectively. That's why we have the HCCL library. It's also similar with NVIDIA's NCCL. Okay. The first is we have some communicator, for example, the audios together, and also some we provide this kind of features to developers. The second one is they also provide the task scheduler. In this way, developers don't need to care about how the operators runs and how to make the operators runs in a quick way. The last one is about high performance concurrent computing communication. You know that with more card or more machine, there's two actions. It's very important. The first one is the calculations in each card. For example, if every operators runs in each card, it's for calculation. The next important thing is to sync data between different cards. It means communications. So there's a way to speed up it, to run calculations and communications in parallel, so that communications don't need to wait for calculations, and all the computer resource, all the network out can be filled up fully. The last one is for the operator level. This means this part. Operator levels. So you know there's much operators. In previous years, especially for the small models, maybe you know that there's maybe more than 100 operators in one model, just in one model. So in this case, users need to write the operators one by one. It's very difficult for developers. In recent years, since the large language models become popular, you can say that although the models become bigger, but the numbers of the operators become small. For example, maybe there's only 10 or 20 operators in one large language models. So in this case, can provide all the operators the models, which the models need, so that for different kind of large language models or the incoming models, the models can be run on Ascend directly. So this table shows some examples. For example, the flash attention, the page attention, and so on. And some operators use the weather. Take a look at example. Need to describe more here. Additional information is that more and more operators downloaded and all the operators are open source. And I also welcome developers to write their custom ops and open source to the world. Okay, that's the brief introduction about CANN. It contains mainly contains four important libraries. So based on the CANN, we also build an open source ecosystem to let users to use Ascend hardware easily. It's from models applications and into toolchains and into accelerated libraries and into the AI framework. For example, I list some famous or popular libraries on the website. You can see that, for example, the Hugging transformers, Taft, Accelerate, and they already supported Ascend. They supported Ascend already, and so that users can use Ascend hardware without any change on this kind of libraries or applications. Especially for the developers who built the models with PyTorch or run models with VLM, they can use Ascend directly. Okay, the next part is Ascend best practice of automated inference and training performance, training and communication. So I just, like I said before, there's a lot of libraries or APIs because on this and here, due to the time limit, I just take VLM as an example because I'm very familiar with this framework, and I also run the VLM Ascend antenna. Okay, so what is VLM? It is created by UC Berkeley Sky Computing Lab in 2023. It is easy to use and high performance open source full stack inference service framework. So it is mainly used for inference. Users can run large language models on with this framework effective and quickly. In 2023, this library is famous for its page attention algorithm because this page attention can help users to save the memory usage and speed up the inference speed. And after 2 years developed, this VLM becomes the most popular open source inference framework in the world. Actually, I can say that maybe it is number one open source inference framework. And with about in this year, February, we start to support Ascend into VLM. And now VLM Ascend is one of the sub-official projects under the VLM community. I'll describe this architecture detailing next. So for VLM, I'd like to introduce some key features about it to describe why it is fast and why it is useful for inference. The first one is for the diversity of the hardware. You know that there's many acceleration hardwares now in the world. Okay, the most famous is GPU. but there's also some others. For example, for the Google's TPU, and for Intel's HPU, and for Ascend Paris MPU. And the different consumers need to run some different scenarios. So users usually want one framework or one library and run all of them together. So we are about these features. So the core issue, different hardware platform have different architecture features. Okay. Operators, as I said before, such as page attention, flag attention, and netball, and so on, they are implemented in different hardware with different ways. So we can't to write a common achievement for different hardware. So in this case, we are provide a machinized to support different hardware and for different attention pattern. Attention is the most important part in large language models. So in this case, we are support CUDA, ROCL, and CANN, and so on. You can see that there are some scheduler, executor, worker, model runner, and this is some concepts in the VR. So maybe we just ignore it. The next technique is a continuous batch. It is why we need continuous batch here, especially for inference, especially for AI scenarios. You know that there's a big difference in AI inference is that the input or the output, the length of the input or the output is not always the same. For example, I can ask the models who are you? It's just a 3 words. Or I can ask the models, can you tell me some concepts of the book? Okay, the book is very long. So in this case, we can't know the length of each input and output. So in traditional batch, we usually set article length. So in this case, there's a lot of space. So the resource is this. So we need a dynamically to make the compute resource or the memory resource to be used fully. That means continuous batch. It means one inference is over, it will start the next inference directly without any wait, without any space waste. And on the right side is that how well we achieve this continuous batch. I take an example here is that we suppose there are three inputs. We call it P. P is the profile in AI inference. Or you can also take it as a prompt. Okay. So the P, for example, there are three inputs. The first is the length is 3. The second one is the length is 5. And the last one is 12. But the scheduler step or the length of scheduler limit is 10. So in this case, how Xiyuan did the scheduler, or how Xiyuan did the inference. First step is step 0. Okay. The principle is that will put the prefill input as much as it can. For example, the length is 10. It will put the first one 3 and the second one 5 and the last one 2 into the first input schedule. And in step 1, the second one, prefill is stopped. The language, the models will output some content. For example, who are you? The next one, I am I. The D is decode, it's decode, it's I. And the yellow one, the second D with yellow color is the output of the second requirement. And you know that the length is 10, so there's also 8 for the third input to do its prefill continuous. So you can say in the step 2, there's also that 2 prefill, and in the step 3, there's no prefill, and they are all decoded until that the language models think the answers is stop. So in this case, you can find that we will use the continuous batch to complete every request for it, so that the compute of the memory cannot be wasted. So the next technique is page attention. It's the other concept is KV catch. I'm not sure if you know about it. I'll explain it in simple words. In traditional attention machines, KV catch needs to be located in continuous grid block. Okay, so you can find that the some of the memories will be missed because it's similar with the continuous batch. Every sequence 1, sequence 2, or sequence 3, the length is not the same. So some cases are missed. So in this case, page attention is split the memories into many small blocks, and each token or each input word can be located in the small blocks, so that the memory can be used for it. And another case is that if there's 2 persons input the same word, the catch can be reused. For example, they both ask the question why, and then the KV catch for this input can be cached just in one place to save the memory. This is a brief introduction about this page attention. Okay. And now more and more AI inference framework support this support page attention already, so that you can see this is a very useful and important technical feature. Okay, the next one, I just said before, single card inference cannot meet the requirements for installation and fast push. especially for the parameters of the large language becomes bigger and bigger. Okay. For DeepSeek V3, there's 600 billion. So one card cannot possibly this case, so that we need classify. And some parallax technique. There's mainly currently there's mainly four kind of the parallax. The TP is the tensor parallax, and EP is the pipeline parallax, and DP data parallax, and recently the most popular parallax is GDP tensor parallax. There's no time to explain to describe more detail here. I just show you that we support all kinds of these parallax features. And the next one is graph mode. I just described the graph engine of CANN. So for the graph case, there is also some usage in the header framework APIs. For example, in VLAN, it means graph mode. And in GPU, in VLAN, they also support graph mode. Maybe they call it CUDA graph mode, graph, and this also called some piecewise graph, and so on. So result graph, I just said before, each operations in the computing graph need to be scheduled and need to the data transfer. It will list calculations and boundaries. So we can